All right, welcome back everyone. Let's look at the solution to the Now You Try problem on an application where you can factor a trinomial. We have a rocket launched off the edge of a cliff 108 feet above a valley below. Its initial vertical velocity is 132 feet per second. The downward acceleration of gravity is negative 32 feet per second squared, the negative indicating that gravity is pulling the rocket downward. The height of the rocket can be modeled by capital H of t equals negative 16 t squared plus 132t plus 108. That space is bothering. Where t is time in seconds and h is height in feet. Answer the following questions. We're going to begin with what is the vertex of the function capital H? To find this, we'll start with the t value. The t value of the vertex is going to be negative b, so negative 132 over 2 times a, 2 times negative 16. This will be 132 over 32, and we'll just start reducing. 132 over 2 is 66 over 16, then we'll get 33 over 8. Not the prettiest number here. We need to plug that back in order to get the height at that time. So I'm going to use a calculator. Let's pull up this, and that's an old problem. We've got negative 16 times 33 over 8 to the second. And we want to go plus 132 times 33 over 8. And then we want to add 108 feet to that to get, let's get an approximation here. $380.25. So our vertex, in fact, the 33 over 8, let's just see what that is also. $4.125. So our vertex is the point 4.125, comma 380.25. That's saying that 4.125 seconds into its flight, the height of the rocket reaches its maximum of 380.25 feet. All right. I'm going to start getting a coordinate plane set up here. I don't know how much information I want to put on it yet. I'm going to kind of think about it. We want to get that vertical intercept in its mirror point. We might even decide that we want to get the horizontal intercepts as well, but I think I can get a vertical scale at least. I want to get maybe 400 on here. So if I put 400 up here, and I don't know, let's go by like 5 of them, so by 20s. This would be 300, another 5, 1, 2, 3, 4, 5, there's 200. Get plenty of height on this. There's 100, and then 1, 2, 3, 4, 5, there's the ground. Not sure what the time is going to look like yet. We haven't gotten any. We have the 4.125 seconds for the time where we hit that maximum height. So our time's definitely going to go out to at least 8 something, probably more like 10 some odd seconds, if not even more. So let's do a little bit more work before we worry about the horizontal scale. I do want to note that capital H is in feet, time is in seconds here. The vertical intercept of h is going to be when we plug 0 in for time. That's going to give us 108 feet. And its mirror, let's find that. Let's mark that 0 and 108 feet. These are going by 20, so that's about here. So an initial height, the rocket's initial height. At launch is 108 feet. The mirror point is going to need to be, well, we had for the x or the t value of the vertex, it was 4.125. So if we double that, we'll get 8.25, comma the same height that we start with there, 108 feet again. So 8.25 seconds into its flight, the rocket has fallen back to 108 feet in height. All right, that gives me a good idea that I need to at least be out to 8 seconds here, 8.25 seconds. But let's figure out where it hits the ground before we get a final answer for how we want to do our horizontal scale here. So to find the horizontal intercepts, we'll set the height to 0. 0 equals negative 16t squared plus 132t plus 108. And we want to factor this to try and solve for t. So I'm going to begin by pulling out a negative 4. I think that goes into everything. Let's check. That would give me a 4t squared. 132 divided by 4. Divided by 2 gets 66. And then divided by 2 again is 33. It should be a minus 33t. And then 108 divided by 4, that would be 54 and then 27. And it will be a minus again because we pulled out that negative. All right, and then we can really ignore that negative 4 in front. So I'm just going to rewrite this as 0 equals 4t squared minus 33t minus 27. And I'm going to use a guess and check method this time. I'm going to zoom in on this. We've got some trials here. So we can try a 4t and a t. And then we need like a 3 and a 9 to get 27. And we want a bigger number there. If I do a plus 3 and a minus 9, this would give us 4t squared minus 9 times 4 is 36. T plus 3t minus, oh, I got it first try. That was total coincidence. I was not expecting that to happen so quickly. But those add up correctly, so that's our correct answer. That's nice. So 4t plus 3 equals 0, or t minus 9 equals 0. Here we'd get t equals negative 3/4, which doesn't matter for us because that's before the rocket is launched. Or t equals 9. So at 9 seconds it hits the ground. We can say that we have the horizontal intercept at 9, 0. And specifically in context, we'll say 9 seconds into the flight, the rocket hits the ground. And we can label that on our graph now. So we need to go 9 seconds out. Let's see how much room we have. Here's 5, 10, 15, 14, there's 15, 16, 17, 18. Yeah, we can do that. Let's go out a little bit farther here. The 5 would put us here. So if we put 10 at that location, here's 5 at that location. This is 2.5. So these are going by halves. There's 7.5. And now we can start labeling everything. So 2, 3, here's 4. 4.125 is going to be right in here. We'll go up to 380 feet, 0.25. So there's 380. We'll go up to just above that. I mean, we're going to mark it right at 380 because it's so little above that for that 0.25. So this is the 4.125, comma 380.25. And then we've got that vertical intercept already plotted, and then we want the mirror at 8.25. There's 8.5. So 8.25 is right in between those. We'll go up and mark that point at 8.25, comma 108. And then at 9 seconds, right here, it hits the ground, 9, 0. And so we can go ahead and draw our downward facing parabola. Something like this here. Nice. This is h equals h of t, right? The height equals the output of the height function. And from this, we can go ahead and answer these questions. How long is the rocket in the air? The rocket is in the air for 9 seconds before it hits the ground. How long is the rocket going up, and how long is, oops, that should say rocket there. That's a copy-paste error from the previous problem. So the rocket is rising for the first 4.125 seconds. The rocket goes up for 4.125 seconds, then falls for the rest of the time, then falls for the duration, which is 4.125 to 9. That's 4.875 seconds before hitting the ground. Finally, we'll say what's the domain and range in context. The domain is all of the times that it's the time that the rocket's in the air from 0 to 9 seconds, and the range is the heights that the rocket takes on. A height of 0 when it hits the ground, all the way up to its maximum height of 380.25 feet. All right, that is it for this problem. As we can see with these applications, when we get into real-world scenarios and applying math in context, numbers can get real bad real quick. And honestly, these numbers were picked to try and make this problem not too horrible so that this would factor here. So I hope you can appreciate the difficulty that we can run into when trying to really handle real-world situations. I don't want you to be discouraged. I just want you to recognize that as we practice these numbers, it's important that we look at some of these harder numbers because they do arise when we're really doing math for a purpose. So we don't want to shy away from it. We want to say it's okay to struggle and it's okay to be learning, but we want to tackle it and look at getting better and better so that we become more and more comfortable with just handling those rough numbers and getting through the scenario. All right, that's everything for this video, guys. Thanks so much for watching, and we'll see you in the next one. Take care now.